topic. So let me just share the slides. Is it visible now?
Yes.
Okay. So let me just do a slideshow, and I hope now it's okay, right? Yeah. So yes. So the talk for today is basically Softcores for FPGA. So let us try to understand in this talk the free and open source hardware philosophy, right? How are we going to actually go with something like this Softcores and try to develop in our own processor, right? So this is the whole talk. So I am trying to minimize this. Give me a sec. Yeah. So even if I remove it, yes, now it's okay. Otherwise, if I, yeah. So the idea is this, that the agenda would be something like this for today. We'll try to understand the components of a computer and its relation to the open source ecosystem. What are the various levels of representation? What is the instruction set architecture? A perspective based on the complexity. Let us try to understand this in brief. Then what are softcore processors? Microwatt, a brief introduction, and then I will give you links to 2 GitHub sites wherein you can download the Microwatt in its Vhdl form and then try to run it. And I will show a similar demo so that it basically will be easy for you to run on any Ubuntu, right? So this is the whole agenda for the 1 hour talk, and then to end with certain references. So this is how I'm going to proceed. So any questions you can type in the chat or you can ask afterwards as you feel like. So yeah, so let's start. So the idea and the concentration of this talk would be from the computing software development side aspect, right? The software developers are people who actually do coding and who are not good into the details of the hardware, how it's designed, right? All of that. The idea is to make people understand both the things, right? From the hardware perspective, from the RTL perspective, from the Verilog VHDL perspective, which ENC people know, and from the software development perspective, which involves Python and other high-level languages, to arrive at our own processor. Okay. So tomorrow also I would be discussing about a Python toolbox, which will help you to develop in your own digital circuits, right? Initially, people wanted to develop digital circuits, and electronics people wanted to develop in hardware design. So you had to read in a course, still that is needed, but from a computer science perspective, right? Let us try to approach the talk and tomorrow's demo as well. So let us try to understand the components of a computer and its relation to the open source ecosystem, right? So the basic idea is that you are supposed to be developing a processor, right? Now, when you're supposed to be developing a processor, you need to have something which is going to control everything in this processor, right? And then there has to be a program counter, there has to be registers, and there has to be the arithmetic and logic unit, right? So this is the whole overall approach of designing a processor. This we have been studying, right? And we study this, and then we use processors which are available in the market, right? So we use processors which are like Intel, AMD, or Apple Mac. Now you have got M1, right? So something like this. So the idea is that when we know that a processor comprises of these things, right? It has a program counter. We know why a program counter is required. we know that there are various registers. So these are treated to be memory locations, which are to be used by the processor internally. And then you have arithmetic and logic unit. Okay, and then obviously to control all that, you have a control unit. So this is the whole design of a processor. So now if you think from a point of view that you need to develop in your own processor, you need to ensure that all of these things are there with you. Okay, all of these things are there with you. And then you need to interface it with the memory, obviously, because you have to have a program, you have to have something which you want to solve with this computing element. So you have a program and then you have your data, right? So you'll have to interface this processor to a memory, right? And this memory has to be interfaced in such a way that you can give input to this memory and you can read it from this memory, right? So you have this total setup, which basically will allow you to give in some input through the memory to the processor, and from the processor, the output comes through the memory to your output device. So this total thing, okay, can be developed, okay, by anyone now, since the open source ecosystem, open source hardware development is actually now fully open with various processing cores available. So those are soft cores. That is why we are trying to discuss, right, soft cores, which can be simulated. Now, once you develop this type of a system or a processor, you need to actually try to see whether whatever you have developed, right, is efficient, whether it's running before you fabricate it, before you develop the whole processor, right? So you need to test it. So prototype testing or something like that. Where do you test it? You need to put it on a FPGA, okay, so that the generic FPGA reconfigures itself to this type of a processor design which you have actually developed, and then you see the behavior of this particular processor on the FPGA, right? So that is how you simulate, try to simulate and see whether whatever you have done, okay, is basically working or not. So I hope it's clear. The context is that now we have to be in a position to develop our own processors, right? So there are various ways by which you can take the soft cores which are available and then try to use it by modifying it a bit. Let us see in next few slides as to how do we do it. So I hope this context is clear of what we are trying to develop here. Open source ecosystem exists. We know what are the components of a computer. We know how the processor is to be developed, right? And what are the various elements which would be needed in order to develop a good processor, right? So this is how it is all linked. Now, let us try to understand the level of representation. Let's go into a bit of a detail now, right? We'll try to understand from the high-level language programming perspective. Let us say you write a C program, right? Now, when you write a C program, you do something like this, right? You initialize various variables, you use an array, you use matrices, you use so many things, right? So in a high-level language, when you write a program in C, C++, Java, Python, or anything for that matter, it has to be compiled and run on the existing hardware, which is somewhere here, right? So now, there is something which is basically an intermediate thing, okay, before we come to the machine language, right, or the machine level code or the binary code, whatever you say, okay. There has to be an assembly level language program. So there is a compiler, of course. You compile a C program, and this C program gets converted into an equivalent machine level code, right? And this machine level code basically depends on the architecture, okay, of your processor. So here I have written RISC-V. You have got open power core also now, which is Microwatt. So the idea is, from a high level language, we now understand the context of the instruction set architecture, which you have already seen in the previous lecture. So instruction set architecture helps us to convert the basic high level program into equivalent instructions which are supported by that specific microprocessor or that particular computing element, right? So I just give it a name, computing element, right? So now the idea is that instead of RISC-V, which basically is a processor, okay, you can give open power, open core, okay, processor, any other open core processor also, right? So here, this is how it's going to pan out. So when you say that machine interpretation is there here, okay, the hardware architecture description, okay, of how basically that particular machine code is going to run on that hardware, there is something which is hardware architecture description, which is something like this. And then that particular architecture is implemented using these type of logic circuits, or this is the circuit schematic diagram. So now ultimately from this point, okay, ultimately from this point here, 1 minute. Ultimately from this point here, okay, I don't know why it's not working, but anyways, so ultimately from this point here, you are supposed to be in a position to understand the whole flow, okay, which basically runs on these simple logic circuits. So this is what is our idea. Now we have a register file, we have a ALU is implemented like this, and then this ALU is going to run in, execute in some instructions, okay, which are basically there in the instruction set, and those instruction set are encoded basically, okay, so that it can be basically understood, okay, by the instruction decoder. And then you have the opcode, and then you have the operands, and all of this is a bit linked, okay. And I hope from this slide at least we are able to appreciate the link between a high level language, the assembly in between, the machine code, the instruction set architecture, and the logical circuit on which that particular instruction is technically executed, okay. So any doubts till now, or any questions? Let me just see. Okay, so fine then. So we will continue since there are no questions. So we will go to the next slide. Okay. So one question maybe, the FPGA's role is in the hardware architecture description. Okay, so let me tell you this in this way. See, when you develop in something like this, okay, this has to be implemented somewhere, right? Okay, so how does this relate with the FPGA design flow? That's what I'm telling. See, ultimately, what is FPGA? It is basically a array, right? And that array need to be configured, okay, according to whatever you want that array to behave as, right? So this means that, let us say I develop my ALU, I develop my register file, this has to be somehow implemented onto this, right? So how do you put that thing, okay, onto a generic FPGA board is something which is also to be learned, but we are not going into that much detail at present in this particular talk. But ultimate idea is that whatever you design, a register file, the ALU, it has to be implemented on a hardware, right? And how do you test it? So prototyping to some extent, okay, can be done using FPGA, because this particular circuit can change based on, let us say, your ALU design. So if this needs to be changed, it has to be tested somewhere, right? And that particular testing has to be done on the FPGA. So somebody does it like this, somebody puts another, maybe say OR gate or a NAND gate in between here, and he puts it on the FPGA and tests the performance. So the idea is the FPGA's role is in the hardware architecture description. I'm not talking, of course, technically, if you want to say, you can say that, but my point of telling you this is you need to actually implement it somewhere and see whether your processor is working fine or not, to whatever level you have developed it. So how do you test it? That has to be tested on a FPGA, right? How does this relate to the FPGA design flow? Obviously, it is related to the FPGA design flow, which maybe you will cover in the next sessions. Ultimately, you have to basically develop something on a FPGA. So the FPGA design flow needs to be learned, right? And there are various ways by which you can learn, okay? The standard conventional way of doing it, or certain things like now what people are talking of, you can use various frameworks which are available, right? Okay, which has got everything into it. Like you start with LiteX, then you have Vhdl, and then you have so many other things. So the conventional way of designing or developing and having the FPGA workflow has drastically changed now since the open source hardware development has come into play now. Okay, so that we will see in some of our next classes. But the idea is that yes, the FPGA design flow needs to be maintained. We will see some of them now. Okay, yeah. So let's go to the next slide. I suppose this is done. So we're talking of instruction set architecture. You have already heard, right, about the ISA. So now the idea is that you are trying to develop a CPU. So what are instructions? You understand that. Okay, so each instruction has an operation applied to the operands, and CPU's particular set of instructions, right, implements an instruction set architecture. So you have open power, Microwatt, RISC-V, Intel 86, IBM PowerPC, ARM, AMD, Intel 86, okay, IA64. So some of that. Now, when you talk of at a higher level, the number of instructions which you can work with, you can classify the CPU families into two categories, right? One is CISC and RISC. I'm not going into the details of how the CISC and RISC are different and all, but you understand that CISC has got a lot of complex instructions, RISC has got reduced instruction set architecture. Okay, so the RISC philosophy is reduced instruction set. So instead of having a very, very complex instruction, right? For example, VAX architecture initially had an instruction to compute polynomials directly. So an instruction was there wherein you can directly calculate the polynomials, okay, for an equation. So that is a very, very complex instruction, but you had that option in the instruction set. But whereas in RISC, okay, which basically is a reduced instruction set, the instruction set is small and simple. And basically, since it's small and simple, you can actually build fast hardwares using that type of concept, reduced instruction set. And the idea is that the compiler helps you, okay, to do complicated operation by actually trying to do something on simpler instructions, right? So that's what it means. So the way in which the programs are written also differ, obviously, because of the instruction set design and so on and so forth, right? So, okay. So what's a soft core processor? Okay. So this is where the FPGA workflow and everything is linked. So please try to what to say, think about this when we are discussing, and then maybe if any questions are there, you can type in, right? So a soft core processor is one that is implemented entirely in the logic primitives of an FPGA using Vhdl. So I hope it's very, very clear. You are talking of developing a soft core processor. That basically means it is not purely implemented on a hardware or a prototype, but you are trying to talk in terms of a soft core processor, which is implemented, okay, entirely in the logic primitive of an FPGA, because you need to port it to the FPGA to see that particular behavior, okay, and that is done using VHDL, okay. So the idea is the core processor, what we are talking of, does not have speed or performance characteristic of a hard core or a discrete processor, okay. So the idea is that you have a very, very basic soft core processor which is implemented, okay, and it is basically given as a skeleton to you, okay, based on which you can go on designing your own complex processor, okay. So you have a basic skeleton processor, very, very minimal type of a stuff given to you, okay. And then once you get that type of a skeleton processor to you, okay,
actual words of true chain.
okay, so okay, okay, the question is, can we define a soft core processor as a software model of a hardcore processor? To some extent, from the conceptual point of view, maybe yes, yes, but the idea is it is something which can be directly tested, okay, and it can be directly implemented on a hardware. That is what it means. If you are talking of a software model or something, see, ultimately the idea is that this is something which is available for you on a software, which if you want to make it as a hardware, you can do it. That's what it means, okay, in layman's terms, if that is the question, okay. So yes, so a soft core processor is actually something which you can implement it on a FPGA, and that has been done using VHDL. That's what it means, okay. So now, since you get a minimal skeletal stuff with you, you can actually develop, okay, add or subtract peripherals from the SoC with ease. So now let us come back to this diagram again, okay. See here. Yes, what is it? Is soft core processor like an IP core of a processor? Yeah, yes, 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 but it is freely available now, yes. So the idea is, initially, if it was not a soft core processor, it was not open source, right? You had to get the IP core, okay, by paying royalty to the company from which you are getting it. So people used to get it from ARM, okay, and something like that, okay. There were companies which used to do that. So they only used to give you the IP, right? So the same thing. Now come down to this diagram. Here you have this soft core processor, this all on the right side, and certain modifications to this, okay, has to be done by you to develop your own processing element or a processor in total. So you have a soft core which has got certain minimal things for you, okay, and then this all things you have to do on your own, okay, to develop your own processor. You can add in various other peripherals. You can add in maybe a coprocessor, okay, or a GPU to it, or something like that, whatever you want to add, okay. So I hope this is clear. So now, so a soft core processor also offers the flexibility of configuring the core itself for the application. So now, see, instead of FPGA, you can call it as a ASIC, right? So it is basically like trying to solve a specific problem for you. So application specific SOC, something like that is what would be your aim if you want to start developing, right, a processor of your own. So you are not interested to develop a generic processor in the days to come, okay. You have a skeletal generic processor with you, which is, let us say, open power Microwatt, okay, and use that to develop in by adding various peripherals a new processor of yours, right? So for that matter, you can take RISC-V core, you can take so many other cores as well, right? So yeah, so each core, okay, has got its own advantages and disadvantages, right? So that also needs to be kept in mind. So using a SOPC solution also offers flexibility outside the FPGA while designing the circuit board, okay. So since a SOPC exists in a FPGA, the pinout is flexible, which gives the board designers almost freedom with the component placement while meeting the timing constraints. So if the question was during initial question asked, was the FPGA workflow, FPGA flow. So this is how it's all linked, okay. So okay, so let us come a bit deep into open power Microwatt. So Microwatt is an open source soft processor core originally written in VHDL by Anton Blanchard at IBM. So this is an open source soft processor core, okay. So let me just take you to that site. Let me share. Okay. I hope, are you able to see this particular web page?
Yes, sir.
Okay. So this is the Microwatt open power ISA soft core, okay. So the idea is it's very, very minimal, okay. It's very, very minimal. So if you see this total thing in detail, okay, when you talk of FPGA, there is a hello world program here which I will run. I have edited something. I'll tell you what I have edited and what we have done. But the basic idea is that this particular, where is it? Yeah. So this is how it is done. If you see this, see cache ram.vhdl, common.vhdl, control.vhdl, core.vhdl, right? So core flash tb.vhdl, then count bits underscore tb.vhdl, then decode 1.vhdl, decode 2.vhdl, okay. So the basic idea what I wanted to show you here is all soft cores, okay, are written in conventional VHDL, okay, and then they have been now what to say, easily being used by people who are not experts in VHDL and all, wherein you can do the simulation, right? And then you can actually use Dockers also for doing it. And then you can do synthesis, okay, on the FPGA, okay, using Vivado, or you can do it using open source tools, okay? So many of that is available now, okay? Yeah, so why VHDL, why not Verilog? See, the idea is it is available, freely available to us in VHDL, so we are taking it from computer science aspect, right? See, ultimately, how it is implemented is important. I'm not telling that it's not important. Okay, well, it's VHDL, Verilog. Now, in the days to come, maybe when I discuss tomorrow, right? People are not even using VHDL, Verilog to develop in the whole FPGA, right? We use directly Python because Python has got toolbox which will do everything for you, okay, whatever is done using VHDL Verilog, right, using open source tools internally. So yeah, if that was the question, so why it's VHDL, why not Verilog, I have not gone too much into that detail, because ultimately the idea is I am going to get something which can be done easily on a FPGA, right? And if, since it's available, so I don't think that there is a need for again reinventing, but obviously there would be some issues which other experts might be able to answer. But from my point of view, yeah, so anybody who is very deep into the electronics of it, from electronics department, would be able to answer that question. Maybe I'll also try finding it out and get back to you tomorrow. But at present, I feel that, okay, since it's available, it's available. Yeah. Yes. So this is how it is. There is option of running MicroPython. Okay, so MicroPython runs on this, and then you can basically run small programs on it. Okay, and we have actually done something with Artix Artix A100 Vigilant board. We have tested on it, and it works fine, right? So that's how it is. So this is how that is done. So how do you run it? I can show the demo, but before that, we'll just try to cover things and then we will try to come to the demo part. Okay, so if you go into the detail of it and see this, I suppose that this is how the control unit, okay, would look like in VHDL. So this is how it's written, and yeah, so this you can link it, the implementation, you can link it with something which is related to the ISA in the days to come, and then link it to the MicroPython stuff, and then you can start programming. So yeah, so there are certain FPGA cards which are supported. Okay, so this is how it's going to run. So let us try to again into my slide deck. Okay, so it adheres to the Power ISA 3 instruction set and can be run on FPGA boards booting Linux, MicroPython, and Zypher. So these are the things which you can do with Microwatt. So Microwatt, okay, one more question. Whether this code is designed to work in a particular frequency of operation, can it be implemented in any FPGA board? Yes, there are certain specific FPGA boards which you need to use. Okay, the tested one is given in the links, so you have to use that FPGA board. Otherwise, anything which has got your board files in Vivado, I suppose it should be able to run, because we tested it and it ran. Okay, certain issues are there which you need to basically solve, but I suppose yes, if you have got board files, if you have got everything there in the Vivado suite, I suppose it should work. So this is a tiny 64-bit big endian scalar integer processor core implementing a subset of PowerISA 3 instruction set. So this basically means Microwatt is a very, very basic open source soft core. You can go on and add in your own instructions, because this is just a subset of the PowerISA 3 instruction set. Okay, and then as you see in the ISA, okay, of Microwatt, you can have your own instructions also incorporated. So at present, it has got 32 64-bit general purpose registers and 32 64-bit floating point registers. Okay, and the thing which we talked about, that for memory interface, it uses the wishbone. Okay, and it at present has no memory management unit and no floating point unit, right? So that is a problem, in a sense that you can run some small programs, you can run something which is very, very simple, but you need to actually use it for solving a problem wherein you need to run certain complex programs for which you need to have a memory management unit. So you need to develop in your own MMU, right? And most probably we will listen to that in a talk by Luke when he talks about LibreSoc. So this is one of the very, very important things as to why when you want to actually install Linux, okay, and Zypher and something, these are all very, very small, like micro Linux type of stuff, okay, and very, very specific things which are very small. Otherwise, you cannot basically do anything more efficiently if you don't have memory management unit with you. Okay, so this is the implementation of how Microwatt is done, implemented. So this is the diagram. Okay, like you have fetch 1, cycle, then I cache, fetch 2, decode 1, decode 2, execute 1, write back, and then you can do multiply, divide, load, store. Okay, so not very complicated, but this is how this is implemented. So if you see Microwatt core, I showed you in the GitHub page itself. We have got decode types, wishbone types, common, fetch 1, decode 1, okay, all implemented in Vhdl. So then execute 1, load store 1, mmu.vhdl. So many things, but you need to develop it. So I am showing you certain things wherein we can actually execute it on a specific board, and we did it on the board, okay, as I told you, by using okay, Xilinx, and we use the Digilent board. I told you that. So we have been able to implement it successfully, and the bitstream, we could port it onto the FPGA and it ran. Okay, so something like this. So these are my references, but I'll show you the demo now, a bit of it. Not going into the details of uh, one minute, give me a sec. So there is some system preference. Okay. So let me just share with you. Okay, so I hope this terminal is visible and the size, font size is okay. Increase it a bit of it. Okay. So, okay. So now let me just show you what is there in this. Sorry. See, this is what is Microwatt, right? So I have done the same steps. There is another thing which you can see of implementing it. Okay, there are so many websites which will help you to run this on Ubuntu or Debian or whatever type of Linux flavor you have. So this is how basically your this thing is, right? The Microwatt from the GitHub looks like. And then now there is something which you need to install, which is MicroPython. Okay, so MicroPython basically is a very, very small miniature, okay, type of what to say, Python distribution, which you can run it on very, very small processors like, or the soft code like this. Okay, so there are two things which we are trying to do, and we'll try to run a C program. You can write a Python program and see it and run it. Okay, so there are 2-3 things which you can do. So what we have tried to do is we use the GHDL also. Okay, so you will have to use GHDL, open source, and then you need to actually have this PowerPC 64 Power 8 glibc, that basically is a cross compiler which you need to install. Okay, so you need to install GHDL, you need to install the cross compiler, okay, and then MicroPython and Microwatt, okay, to see how this works, right? So let's go to hello world now. Let's go to my quad. Okay, so here you have got this hello world, and now these are certain things which you have written. You can just see, and then you have converted it into a hex file. You have got the ELF and you have got the bin. Okay, so which packages you will have to install in PC? So the idea is that I am working on Ubuntu, right? So on Ubuntu, okay, you will have to install, before you install Microwatt, you have to install MicroPython, GHDL, okay, okay, and other things, right, which are there in the link. So this is what you're going to install. If you go to that link, right, the whole flow is given you. Please do step by step, okay, and then you can do things very easily. It's not very complicated. once or twice in the beginning, you might feel that it's nothing is happening, but these are all certain small issues, like some packages would not be there, or there would be some dependency. Okay, if you install it, it's going to serve the purpose. Okay, so nothing very difficult, but of course, once or twice you have to attempt it, it will come, no issues. Yeah, so people are asking of whether you can do it on WSL. You can do it on WSL. Yes, you can do it on WSL. I have now today I'm showing it directly on the Ubuntu, but you can do it on WSL. Yes, you can do. I have tested it. It works fine. Yes. Yeah. So I'll share the link. 1 minute. Let me just copy that link and put it on the chat. Yes, I have sent that link. Okay. So now, so I hope you understand that we have the ELF, we have the bin, we have the hex, we have the object file. So this hex file needs to be burnt directly onto the FPGA board. Okay. Or you can do a simulation. Okay, so see, please read the document. It is not just downloading. You have to install certain things step by step. Okay, and the first thing itself tells you about Python installation. The video itself is a GIF video. Okay, and then how to do it step by step. I'm not telling you to just download. Yeah, you will have to install. Yes. So let me just show you something on this Microwatt, a simulation of a C program, okay, which some of my students wrote. Uh, let's see. Yeah, so this is something wherein those people have tried to actually, okay, print in some numbers, okay, and then they have put in their names. So this is just a small program. So we are going to run this program on the Microwatt simulator. Okay, you can actually port it onto the FPGA and run that also, but at present I am trying to show it on a simulator. So let me just show you that. So, oh, yeah. So see something like this. Okay. So this is running on the Microwatt now. Okay. So this is a small C program. So that's it. So I suppose I'm done with it. Any questions? If you have, I would be very happy to answer. But this is how the overall Slack link is it? So, okay. So which file goes to download in Microwatt? Okay. Okay. So let me show you there itself. 1 minute. I could have shown it, but that board is at a different place. So even if I run it, you would not be able to see it. I should have actually put in the video. Then it would have been nice. 1 minute. Let me check if I have that video. I'll share that with you. But the idea is that I'll show you which file will go, okay, and how it's going to go. Give me a sec. Okay, so here, see here, if you are directly trying to put it, okay, on the board, okay, so you should have the installed Digilant files, and then we had Nexus A700T, okay, instead of Nexus Video we had Nexus A700T. So we did this, okay, and then you will have to actually put this hello world.hex, okay, onto the FPGA. So it is basically a hex file which you port and then you basically run it. Okay. So if you run it on the board or the simulator, for this particular example, see here, you have done everything. So you run MicroPython. So I showed you a bit of a C program so that people can correlate, right? Instead of just Python. Okay. So if you run this, if you follow these steps, you will be able to run a Python, MicroPython, and you will get the Python command prompt, and you will see that it performs certain addition operation, a very, very preliminary Python operation. So what we tried to do was we tried to show you C program which runs on the simulator, as well as you port that hex file onto your FPGA using the Microwatt, and that particular thing executes a C program, but a very, 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 very minimal C program. Okay, very, very small C program, not very complicated. You cannot do many things, right? Because of the absence of the MMU. Yeah. Yeah, so which packages are to be installed particularly on Ubuntu? You have to install MicroPython and Microwatt. And before you start installing them, you have got this tool chain to be installed, okay, which is a cross-compiled tool chain, okay. So if you read this, you will be able to understand everything, okay. Yes. Yeah, I have shared this link. I have shared this link in the chat for everyone. Yes. Okay.
Yeah,
So
Professor Satya, actually, uh, what I'm thinking is maybe next time we can have a one-day program where 2 hours training on this microwatt implementation on FPGA, and then give the 5 to 10 FPGAs to the students, like the students team, like the 4 people per team or something, to go and implement it. The
yes,
same thing. That kind of competition, we can have it. Maybe not one day. It's basically, we can give it 2 hours training, and probably we can give a technology advocate throughout the period. Maybe 1 week time, we can work with the professor at BIT and plan
yes,
for a kind of a hackathon.
yeah. We
Go
can
and
do it. No
go
issue.
and break your the best people, who are part of this team. We can plan, and we can start working on a kind of a little. It's not a hackathon, basically a kind of go learn yourself, and I mean go and deploy the microwatt in a FPGA kind of a program we can announce.
Yeah.
Madam, what do you think about it? Real line, madam?
Yes, sir. Yeah, that would be fine, sir. We shall plan for.
Yeah, because we put a lot of effort on this workshop, right? Outcome of the workshop, one of them is actually basically people should learn about Microwatt completely and then go and deploy. Like, there are questions about, what are the various tools used for deploying these and all. Everything will be
Yeah,
like,
we can plan for some competition kind of stuff.
yeah, sure, madam. Like a 5 people in a group or something, like a 10 groups we can select, and we can do that too. Okay.
Yeah, sure, sir. Sure.
Yeah, as a follow-on to this workshop, note it down actually. Maybe,
Yeah, yeah.
yeah, our volunteer team also like can announce that later on. Put together. Well, this is possible though. We can do this. Okay, sure.
Okay, sir. Yeah.
Yeah, thank you, Professor Satyanandan. This is very good, useful information. Whatever you are sharing here, a lot of question and answers. On the
Yeah.
chat window too.
Yes.
I think maybe you should continue a little bit about this in our next tomorrow's meeting also, along with your other presentation.
Yes, we'll try to do it. Yeah, let me see. So the time, but anyways, yeah. So one or two questions here, like, can we run a simple program to understand? This is a very, very simple program. See, what I have run is a very, very simple program. It's just incrementing. More than this, you cannot do it on this particular core at present, right? Because you don't have the MMU over it. So you have to have a lot of memory, right, to access it and then do things. So here it's a very, very small program, very small C program, right? You don't have a lot of things also. So you don't have something like this. But when people ask me as to what will be the advantage of using a microwatt simulator over implementing it on an actual FPGA board, see, ultimately simulator is just to test whether everything works fine or not. But the actual thing is it has to be on the FPGA board, because tomorrow, let us say you have to do scanf, right? Or take the input from the user, right? On the simulator, maybe it becomes very easy for you, but when you actually port it onto the device, since you don't have anything else, you have to actually link it to the TTY, the terminal, and so many other things you will learn, right? So that is what is to be done. You have to put it on an FPGA board to actually feel the thing. Okay. Yeah. So I suppose there are no other questions. So I stop. Yeah. Thank you very much for the opportunity given. Let us see how we can further collaborate on stuff and then try to do some good workshop hands-on. Yeah. Maybe physical or something. Let's see. Yeah.
Yeah, Jugi, go ahead.
Yeah, so that's it. So can you please write one simple program and execute so that we can clearly understand, sir? Yeah, okay. So let me just show you, like, yeah, we don't have time, but anyway, let me just try to do it. Let me show you, right? So let me show you. See, first thing is you have to understand the context that a microwatt is a soft core. It's a small processor. Okay, and then you have this MicroPython also installed, and now I'm trying to write a C program, right? And what is the C program which I'm trying to write? C, right? So this is, let us say, right? So this is a C program. What are we going to do, right? We are going to actually do this. I'm incrementing the sum and printing the sum, and I'm just, okay, trying to do this operation, right? So how do I
Sir,
print
are you
it?
sharing in the program? No. We can
Oh,
see the list of
it's not
various.
visible, is it?
Yeah,
Oh,
we are.
sorry.
We see the list of
Actually, I
various.
thought that everybody has seen that C program, but okay. No, wait. I'll share. Oh, that is the reason why. Okay, so this is a small, I suppose now it's 1 minute.
Yes, yes. Yeah, now the code is.
Now it's visible, right?
Yes, yes.
Okay. So this is a very small C program, right? What have we done? We have not done anything much. Okay. We are just putting the character. We are creating a function I print. Okay. And then using that, okay, to give some input from I, okay, incrementing that as a sum, just I to 10. So basically forget about all of this if you are very confused or trying to understand. Just see, we have just put this put s, right? Printf is not possible here still now, because we have to put it as a string and just the small character wise, right? So this is what I just wanted to tell you, that printf is not working, scanf is not working. Very, very small minimal things we have to modify and work. So here just think that you have put some names, right? And these are some student of mine who have done it, so they have got their exams. Otherwise they would have also shown something. So this is how it is. So what we do, see, ultimately what are we going to do? We have this bin file, right? And we have this command here. So let me just show you how we are going to link it. See here, we are linking the building it like this, okay? Firmware.bin, main ram.bin, okay? Then trying to use a pre-built image and then trying to actually run it on a microwatt. Otherwise you port it and put it on a hex file and then port it to your FPGA hardware, right? So this is how it's going to be panned out, right? So yeah, we can do it in detail, but just in 1 hour you cannot exhaustively do it. So that's it. Okay, so thank you very much. Thanks everyone. Yeah, so I
Thank you,
stop.
sir, for the insightful talk.
Yeah. Do you want to?
Ganeshan, sir, can we convene after lunch at 1:30?
Yeah, please go ahead.
Thank you, sir.
Yeah,
Yeah.
go ahead
Bye.
and convey, Zugi.
Thank you, sir, for the insightful talk.
Yeah, sure. Thanks a lot. Thank you so much. Yeah, pleasure.
And yeah, Zugi, go ahead and convey about the lunch break and when people should be back.
Yes, please go ahead for lunch. We'll start again at 1:30.
Thank you all.
Thank you.
Yes. Yeah.